Hey, Keegan, what's the title of this lesson? Funny. Okay. What we want to look at are two interesting space phenomena. The first one does affect us. Asteroid impacts. There have been many in our history, at least one massive one that wiped out most of life on the Earth. So, suppose a 45,000 kilogram asteroid, not very big, is traveling at 5.67 times 10 to the 4th meters per second at a distance of 1.2 times 10 to the 7th meters from the center of the Earth. Lena, from the center of the what? That's a radius, not an altitude. If they had given me an altitude, I would have had to add the radius of the Earth to turn it into a radius. How much kinetic energy would it have if it impacted the Earth? Well, I can't just go a half m this v squared, because as it falls, what's going to happen to its speed? Increase, decrease, or stay the same? Okay, you know what? This is a job for conservation of energy. So let's go like this. KE initial plus PE initial equals KE final plus PE final. Unfortunately, none of these are zero. We're not starting at rest. When we hit the Earth, we're definitely not stopped. And are we out at infinity at all? Okay. We want to get KE final by itself. So I think the first thing I'm going to do is go KE initial plus PE initial minus PE final. That equals KE final. All right. What's kinetic energy been since day one? What's our equation? Half mv squared, so that hasn't changed. It's going to be a half mv initial squared plus mg. Oh, no, not mgh. We're cosmic. Negative big G, big M, little m over R initial minus negative big G, big M, little m over R final. That equals the final kinetic energy. All right. So it's going to be 0.5 times 45,000 times 5.67 times 10 to the 4th squared minus big G, big M, 45,000 all over. I guess our initial distance, Nick, is the 1.2 times 10 to the 7th. And then I have plus same thing times same thing times same thing. What's our final radius? Radius of the Earth, that's what we're getting. So 6.38 times 10 to the 6th. That's going to be my final kinetic energy. I think, again, this is where my love of getting stuff by itself ends. I'm going to find this term to 5 sig figs, this term to 5 sig figs, this term to 5 sig figs. I'll probably backspace and edit for these two. Okay, so here we go. 0.5 times 45,000 plus times 5.67 times 10 to the 4th squared. I get 7.2335. That's a good place to round off because it's a 0 times 10 to the 13th. Is that right? 7.2335. 7.2335 times 10 to the, what was it? 13th. Holy smokes. Minus 6.67. Scientific notation, negative 11. 5.98, scientific notation, 24 times 45,000 divided by 1.2 times 10 to the 7th. For the second term, you get minus 1.4957 times 10 to the 12th. 1.4957 times 10 to the 12th. And then plus, I can backspace and edit. I think I just need to change the radius, 6.38 times 10 to the 6th. And again, I can't emphasize enough, all of you, I hope, are trying these on your calculator, because these are ones kids constantly on the test. Oh, you got all the right numbers? Wrong answer? You were too lazy to follow along during class. I just have no use for that. Third term, I get 2.8133 times 10 to the 12th. That's going to be my final kinetic energy. So, the final kinetic energy is going to be 7.2335, scientific notation button 13, take away 1.4957, scientific notation button 12, plus, answer button. I can do that at least. And we have, Jan, what'd you get? Have you been typing along and following along like I strongly recommended? Yeah? Are you lying? Yeah. Take my hint. Right, Alex? Okay. Now I'll go to 3 sig figs. 7.37 times 10 to the 13th joules. Is that a lot? I don't know. I mean, it seems big, but I also know 1 joule is not very big at all. So I did some research. If you look on the next page, the atom bomb that exploded over Hiroshima, the first atom bomb, had about 6.3 times 10 to the 13th joules of energy. This would basically be a small atom bomb. Not a good day for whoever's beneath it. Okay? How fast would it be traveling on impact? Well, I know that kinetic energy is a half mv squared, so I guess v is going to be 2 times the kinetic energy divided by the mass. And then, Maddie, what else should I remember to do? Okay. You know what? I'm not even going to write the numbers because it's been a long lesson. It's a Friday. I'm going to go 2 times answer button divided by, what was the mass? 45,000? And then I'm going to go square root answer button. 57 kilometers a second. 57,200 meters per second. Now, this is ignoring air resistance. It's true in real life. A lot of this would get burned up in the air. You might remember about 10 years ago, there was a meteoroid that exploded over Russia, and it did a lot of damage. There was a lot of dash cam footage, and the shock wave was enough that it shattered windows. And so, of course, because light travels faster than sound, a lot of people saw the bright flash, went to go look out their window, what's going on, and a few seconds later, their windows shattered. A lot of them got glass slivers in their eyes and had to go to hospital and get them taken out. So, for what it's worth, if you see an asteroid explode in the sky, get away from glass. You'll have a couple of seconds before the shock wave hits you, but you don't want to be near glass. That's a fair bit of damage. That's a fair bit of speed. So asteroid impacts. Do we know that one happened in the past? We're fairly confident that that's what wiped out the dinosaurs. And of course, you all know about the football stadium-sized asteroid that's going to hit us in 2036. You don't know about the football-sized football stadium-sized asteroid that's going to hit it? Wow, are you uninformed? Put your pencils down, look up. By the way, 45,000 kilograms, that might be maybe the size of my classroom. So a football stadium-sized asteroid would have a great deal more mass, okay? Let's talk about asteroids.
Yes, in the middle. Just speak up, and you won't need the microphone.
Hi, I'm Deja. You spoke about an asteroid coming towards Earth.
Well, she didn't forget that asteroid, did she? She didn't forget the asteroid. So you want a quick update on the asteroid? There's an asteroid the size of the Rose Bowl,
Football stadium.
headed towards Earth. It's called Apophis, named for the Egyptian god of death and darkness. It wasn't coincidental that it was named that. When this asteroid was discovered in December 2004, its trajectory was calculated based on a short segment of its orbit, because you look from one day to the next, it's in a new place in the sky. These folks are moving. Once you saw that its trajectory would intersect the orbit of Earth, you don't name that asteroid Bambi or Tiffany, right? You're going to give it a name befitting its...
Some sense of gravity.
Yes. No pun. Yes. That pun was surely intended. The reason why you never heard of it, perhaps, is because it was discovered that this aspect of its orbit was calculated and reported on the same week of the Indonesian tsunami.
You're too young to remember. What year were you all born? Yeah. So in 0405, I think it was 05, the year this happened, this asteroid was discovered right around Boxing Day of that year. On Boxing Day of that year, there was a massive earthquake in the Pacific Ocean, and it sent a tsunami over Indonesia that wiped out 250,000 people. Okay? Is that a fair number of people? Yeah. Entire small islands were wiped clean. Nobody left. Gone. So, of course, Jan, who's not staring at his phone right now, because that would be the ultimate in foolishness, this did not make the news. Well, or if it did, it was page 40.
Okay. I think it was end of 04 or 05. I forgot which of these two
End
years
of
it
04,
is.
I think it was.
Same week. Odd thing is, of course, that 200,000 people died in that tsunami. Odd thing is, if this asteroid hits in a place where it could hit, and I'll describe that in a minute, it will hit in the Pacific Ocean, it would create a tsunami in the Pacific Ocean that would make the Indonesian tsunami look like a street puddle that slightly overspilled its edges. So I think rightly the media attention was given to the Indonesian tsunami, but that was not an excuse to then never have the press talk about this object. It's a real object. And there's something called the keyhole. It'll have a close approach to Earth in the year 2029, in April 13th, which, by the way, is a Friday.
So on Friday the 13th, April 2029, how old will you be? Do the math. Do the math. Oh, that's your birthday? Yeah. Okay. Do the math. How old will you be? Okay. I guarantee it will make the news front page headlines then, because it will be dipping beneath our communication satellites. It will be by far the biggest astronomical object to swing that close to Earth. Friday the 13th.
It will come close enough to Earth to dip below our orbiting communication satellites. For that passage, that will be the closest, largest thing we have ever observed in the history of our observing the universe. That's a shot across our bow. The uncertainty in its orbit at this moment is such that for that passage, there is a range of orbits it could have, which, if it goes through what we're calling the keyhole, Earth's gravity on it will be just right. Or rather,
Just wrong.
just wrong. That the next time around, it will hit Earth. 7 years later, April 13th.
Happy birthday.
If it goes to the center of the keyhole, it'll hit the Pacific Ocean 500 kilometers due west of Santa Monica. It'll plunge into the Pacific Ocean to a depth of 3 miles. At that depth, it will explode, cavitating the ocean with a hole 3 miles wide, 3 miles deep. That impulse will send a tsunami wave that will basically wipe out the entire west coast of the United States and the east coast of Asia. Now, oceans don't like having big holes in them. So this 3-mile-high wall of water does what? It's a hole in the water. What does it do? Falls back in the hole. This is not Moses here. We're talking... It won't just stay there, like in the movie. It'll fall back into the hole, slosh into itself, rise high into the air, fall back to the ocean, cavitate the ocean again. And it'll do this with such ferocity, it'll repeat itself about 50 times, taking about an hour. So every time it cavitates the ocean, it sends another tsunami. So it won't be just one wave like the Indonesian tsunami was. This will be 40 waves, 50 waves. Now, each wave has to pull back out to get ready for the next one. And they're separated by about a minute. So there's a limit to how far these waves will get on shore. We think it's about a quarter of a mile. So if you're more than a quarter mile inland, you can just watch this happen. If you're not, now, the $1 million Malibu homes, they will feel this first tsunami wave. The tsunami will basically pick up the homes. It'll bring them back out to sea. Then the next wave will come and return the home to the shoreline. But now the home is in a slightly different shape. And as this continues, all man-made objects along the coastline and trees and debris basically becomes this churning, ablative mass, wiping clean the entire coastline. Now, nobody has to die, because we'll know this well in advance. But I found there are two people who will die. There is the stupid surfer who says, I gotta do that tsunami wave, dude. You know they're gonna be out there. Okay? So we'll have dead surfers and dead weathermen. You've seen them. There's the camera guy over there. Come closer. Watch the hurricane slash into the... Get this shot. Can you see this? I'm reporting from the hurricane. Now, I'm a scientist. If this asteroid goes through the keyhole, there'll be people evacuating the West Coast, building shelters, stockpiling food. There'll be people praying to their gods. There'll be people doing all kinds of things. I'd rather be doing something about it. This is where engineers come in, and physical scientists, and physicists and astrophysicists. So, we've got top people right now working on a way to deflect the asteroid. Therein is the power of science. You don't have to build a shelter from something that could kill you. You can prevent the thing from killing you in the first place. It's like, how do you solve acid rain? Let's have acid rain-proof umbrellas. No. You want to stop the rain, all right? How is your brain wired for finding solutions? So, there you have it. So we'll monitor the news at that time. By the way, it is not known who will pay for that deflection mission if it comes to pass. Probably America, but asteroids can hit anywhere in the world. In the UN, while there's a space unit of the UN, there's no funding stream. Suppose this were headed for Indonesia. Would we pay for that to deflect it? And suppose we pay to deflect it and we only half deflect it, and then hit somewhere else. That's an interesting geopolitical problem. So it's not just fix it and go home, it's more complex than that. Well, by the way, you got these guys who stockpile nukes, and that community want to blow the stuff around the sky. There's the folks who want to use the nukes that we have. And the problem is, here in America, we're really good at blowing stuff up. We're less good at knowing where the pieces go after the explosion. Whereas when you deflect something, you can monitor your progress all along. But another question?
So that was from about 8 years ago. Since then, we have got better data on Apophis. We've been observing it because it did catch scientists' attention. And the likelihood in 2029 of it going through the keyhole is extremely unlikely. It's not zero. You know what? It's zero. It's not technically, but Quinn, enjoy your birthday in 2036. It'll be good. Okay. But I'm telling you, in 2029, it will make the news, because that will be a very, very large asteroid coming very close to the Earth, and it will make the news then. And it's not an excuse for not paying attention. I don't know if any of you saw quite recently, NASA and the European Space Agency, they had a mission that they called DART, D-A-R-T. It was an acronym. Basically, they tried to deflect an asteroid, a tiny one, and they did it just by firing a very, very fast piece of a big mass against it very fast. And it did deflect it. They were hoping to deflect it. I need to look up the numbers again. They were hoping to deflect it, I think, something like 4,000 or 5,000 meters. It looks like they managed to deflect it 35,000 meters. So the theory seems to work. We do monitor asteroids, and the idea would be the sooner the better to deflect it. If you're driving a car and a person is 1 meter in front of you, for you to miss them, you have to do hard turn. But if they're a kilometer in front of you, you barely have to move your steering wheel like 2 degrees and you'll totally miss them. So the sooner we can catch it, the better. Point being, nothing makes us special. Hey, when you become tax-paying citizens, fund the space program. It's not just because, we want to go to space. It may be essential to our survival. There's a running joke that the reason dinosaurs went extinct is because they didn't have a space program, right? Example 2. Geosynchronous satellites maintain their orbit over the same place on the Earth at all times, somewhere over the equator. What we do is we put the satellite in an orbit so that its period matches the period of the Earth. What is the period of such a satellite? Well, how many hours does it take the Earth to go around? Hello? How many hours does it take the Earth to go around? So if you go 24 times 60 times 60, what do you get? And I think that's what it says on your formula sheet, right? 86,400? Have we lied to you? Does the Earth not go around in 24 hours? Is there not 24 hours in a day? The answer is, it's way more complicated than that. Put your pencils down. This is nerd trivia. When in doubt, use the one from the sheet, the 8.61 times 10 to the 4th, 86,100. However, you may see sometimes in my answer keys, if I was doing an answer key and I didn't have the formula sheet, I might have used 86,400. If you're off on the third sig fig, I might have used that one instead. I need to go, what am I looking for, Mr. Dewick?
I'm back in your face, Chuck.
Well, virtually, yes. Just because you move closer to the camera. It's not as intimidating as it is in real life. And you're a pretty big guy, so in real life that'd be intimidating. But virtually it's just like you're like making a funny face to me.
You know, when I grew up in the street, if people wanted to get in a fight, but if we're going to get into a fight, but you didn't want to fight the person, you'd pretend you were angry and then you were badass, but you'd say, "Hold me back!"
Right?
Hold me.
Exactly.
And you'd run behind people to have them hold your back.
Nobody's touching you, dude. What are you talking about? I said, "Hold me back, man." That's my. I'm telling you, hold me back.
Yeah, it's not I need you to hold me back.
Right, what's your problem?
So he don't hit me.
Right.
So, what am I talking about? I'm going to talk about Earth.
Okay.
Okay?
I like that place.
Okay, so good. So, how long does Earth take to rotate on its axis?
From what I've been told, 24 hours.
24 hours, okay. In fact, we kind of defined 24 hours to mean that.
Right.
So that's how we divide up time. Okay. So as you might have guessed, it doesn't take 24 hours. It actually takes 23 hours, 56 minutes, and 4 seconds. Okay?
Really?
Yes.
Now, wait a minute.
Wait, hold on. So let me just be clear about what I mean.
23 hours.
Get rid of the entire solar system
Okay.
and watch Earth rotate. Okay? And stand there and time it. That spot that's in front of you will come back around in 23 hours, 56 minutes, and 4 seconds.
One full revolution. Okay.
Yes. Okay. That's called a sidereal day.
I like
Sidereal
this.
means star day. So you're measuring with respect to the
day.
universe. Okay?
Nice.
However, we don't base our lives on when stars return to the same spot in the sky, in the night sky. We base our days on when the sun, which also happens to be a star, returns to its spot on the sky. Okay? It turns out that takes longer than 23 hours and 50. Why? I'll tell you why. Because in the time it took Earth to rotate, 23 hours and 56 minutes, it actually moved almost 1 degree in its orbit around the sun. So it rotates back to where its previous line, but it has to turn a little bit extra.
To get back to the same.
A little bit extra to put the sun back in the same spot on the sun.
Right.
And that's a little minutes extra.
That's fantastic.
And why
Oh
did I say
my God, that's just, I love that.
I've only just begun. So that little extra 4 minutes. So I said we move a degree in our orbit each day. I didn't just pull that out. How many days are there in a year?
365.
Okay, and how many degrees in a circle?
360.
Yeah, so it's about a degree a day.
That's about a degree a day.
Yeah, so technically it's 1 degree and 5/365ths.
Oh, wow.
Of a degree. But it's basically a degree a day. And in that degree, you have to turn that little extra. So just imagine you keep having to turn your head.
Just a little bit
extra
more.
amount. Okay.
Because you move just a little bit, so now you got to look back just a little bit.
Correct.
That's cool.
Well, let's keep going. Okay.
All right.
Earth's orbit around the sun is not a perfect circle. Oh, by the way, so the first day is a sidereal day. The second day is a solar day.
Gotcha.
Okay? So for obvious reasons. And they're not the same. All right, now, Earth's orbit around the sun is not a perfect circle.
Right?
Which means sometimes we're farther away, sometimes we're closer. When we are closer, we are moving faster in our orbit than when we are farther away.
Okay.
Okay? That's how gravity works. So, it turns out that extra 4 minutes is not the same if we're farther from the sun than if we're closer to the sun. Because we move more than our allocated fraction of a circle when we're close to the sun and less when we're farther away from the sun.
Gotcha.
Okay? So, the length of the solar day is changing continually throughout the year.
Wow.
And sometimes it's less than 24 hours, sometimes it's more than 24 hours. So sometimes the sun gets to its highest point in the sky before clock noon,
Right.
and sometimes it gets, so what we do is we just average that over the whole year and say, sun, you are average 24 hours, and there you go.
Wow.
By the way, if you ever look at sundials, there's a map on the sundial that corrects for the sun being early and the sun being late. You either add or subtract up to 14 minutes of the day from what the sun time reads in order to get your clock time.
Wow.
All right? Every sundial has it, so it's a figure 8. It's called an analemma. It's got a name, an analemma. I don't want to talk about analemmas right now. So what you have on your clock is the average length of a day over the 365 days of the year. All right, so now we define that as 24 hours, each hour 60 minutes, each minute 60 seconds. Got it. Okay. Well, what is defining this? Well, it's the rotation of the Earth.
Right.
Okay?
Makes sense.
Well, all right. Well, how stable is that? Even in the perfect average that we're taking.
It's house. Well, you'll never know, will you? Because you're using Earth to define the time frame.
Right, exactly.
Okay? If Earth is your measure, and you are slowing down, you will never know this. Just there's no way to know it.
Right.
Okay? Now, back when I was growing up, watches, they would boast, this is how old I am, they would say, get this watch, it's so accurate, it's accurate to 2 minutes a month.
Wow.
Okay?
What?
That was like accurate.
That is
like,
not a good advertising.
Okay, well back then it was because cheap watches were 10 minutes a month. You'd have to you'd set your watch every day. Why do you think heist movies would always say, "Let's synchronize our clocks"?
Right.
Before they perform the heist.
Oh, that's cool.
They knew that the clocks were not keeping good time. Earth was keeping the best time at the moment. Okay, so now you pose the question: maybe Earth is not the best timekeeping device. Let's offload the responsibility of keeping time to something else, like a vibrating atom. So we did that.
That sounds
Cesium, so the cesium-137, there's a electron transition between two energy levels that has a very precise frequency. Okay? Very precise. You can measure. What's good about that is any lab can get some cesium and measure this and then define the length of a second in their lab. Okay?
Okay.
When you do this, you multiply it by 60, you multiply that by 60, you get the hour, you multiply that by 24, you do this, and you find out that Earth is slowing down.
Well, it's kind of old. I'm just saying.
It's been added. It's tired.
It's a long time.
It's tired.
If you're 4.6 billion years old, you can slow down a little bit
You
too.
might be tired
I'm
too.
just saying, you might lose a step when you're
Oh,
getting.
that's very sweet of you, Jeff. That's very geriatrically sensitive of you. So you only would know that Earth was slowing down once you offload it to something else that tracks time.
Right.
And what we found out is that the sloshing of tides on the ocean floor, on the beachfronts, actually works to slow down the rotation of the Earth.
Oh, wow.
Okay, because the moon is causing these tides.
Right.
Okay? And we're rotating faster than the moon is orbiting us. So the moon is tugging on tides backwards on our attempt to rotate.
Right.
Okay?
So it's almost like there's a counterweight.
A counterbalance, exactly.
Yeah, counterbalance that's pulling against what?
Against us.
Wow.
So, tides are slowing down the rotation of the Earth, and in response, the moon is spiraling away from us by a couple inches a year. Okay, that's in response to Earth slowing down. It all relates to what's called the conservation of angular momentum, but it's a big ballet. Okay, and so we've been slowing down, and Chuck, what we could do is say, let's redefine the second, the length of the second, so that we always have 24 hours and 60 minutes and 60 seconds. But that's messy. Right. And every year, here's a new definition of the second, folks. Go to your lab, redefine the cesium atom. No.
It's much easier to accept the fact that, we're breaking up with the moon, but, it's just taking some time.
Breaking up is hard to do.
Everybody has to be on the same page so the breakup can be as amicable as
so
possible.
that's a nice way to think about it. The way we compensate for this is we add a leap second.
When do we? Oh, well, it has to be every 4 years then. We had a.
No. Did I mention years at all? I'm saying days, dude. Days.
Every 4 days?
No. What I'm saying is, we monitor when we have fell behind by a second.
Okay. So when we know that we've lost a second, based on our atomic measurement.
Correct. Then internationally, we
Right.
say, time to throw in a leap second.
Now we throw it in.
By convention, we throw it in on June 30th or on December 31st. And we can throw in one at each time if we needed it, okay?
Right.
Since 1973 or 4, something like early 70s, there's been 24 leap seconds added to the calendar.
Sweet.
So when they're going to add a leap second, they choose which of those days it will be. When they do so, that final minute has 61 seconds in it.
Nice!
Yes, it's very cool. It's very cool. And so this is what we do.
The longest minute of
Yes, it's the longest minute because it's actually 61 seconds.
seconds.
Okay, so newspapers like having fun with this. Say, this year will be slightly longer than other years
Right.
because you have to throw in the leap second. That leap second happens on Greenwich time. So for us, it would take place at like, I guess, 7 p.m.
Right.
4 p.m. Pacific time.
Because we're 5 hours behind them.
Well, the Greenwich Mean Time.
Right. Greenwich Mean Time. Right. So I was at a dinner party once in the June 30th leap second. At 7 p.m., that's when you're having dinner. And I said, pause! I got out the atomic clock, and we just watched that sucker tick. 61 seconds went by. We toasted it with a sip of champagne, and then went on our way.
Okay. Why are you walking around with an atomic clock?
No, I have I have access. Don't just let's
Oh.
not just. I got people.
Okay, right on.
All right. So a couple more things. Other things that can change the rotation of the Earth, not just the tidal sloshing.
Right.
Okay. But here's one for you. You ready?
Good.
Right. You've seen skaters who want to speed up their speed. So what do? Their hands start out extended. And they start with a slight rotation. They bring in their hands and they spin faster.
Right.
Right. What they've done is they've changed where the mass is relative to their rotation axis.
Right.
So the farther away the mass is, the slower they're going to rotate. The closer it is to the rotation, the faster they'll turn.
Right.
Okay. If Earth has an earthquake and one of the continental slabs shifts north, okay, then there's mass on Earth's surface that used to be closer to the equator the day before and has now moved closer to the pole. That will have the effect of speeding up the rotation of the Earth.
Right.
Large animals that migrate, okay, will change where the mass of the Earth is from the northern climes down to the south, and they're farther away from the rotation of the axis. So not only do tides affect the rotation of the Earth, seasonal migration of animals affects the rotation of the Earth, and so does earthquakes, so do volcanoes, and anything else that's remapping the surface of the Earth. And you know what else will change it? The melting of land glaciers.
We're in trouble.
Okay, but you got Antarctica has land glaciers as it melts. What used to be right there near the pole now melts and goes closer to the equator. That will slow down the rotation of the Earth because that's like the skater bringing their hands farther
out.
away.
Right.
So all of these factors combined, basically, Earth's day has been increasing rather than in principle it could decrease depending on what's going on.
Right.
Then I had this diabolical idea. We go set up jet engines, anchor them to the Earth, face them either due east or due west, and ignite them, and then the exhaust would help speed up or slow down the Earth. I thought we might do that. Then I did the math on that, and no, it's not going to work. It's not enough. It's just not enough.
You would have made a good Bond villain, though.
Yeah, it's just, it's like Lex Luthor saying, let me create an earthquake to make
Create beachfront property.
In California. So, yeah, it's geoengineering on a huge scale. But in principle, you could do that. But if you take the greatest engines and fire them, the mass of the Earth is so huge, you just have essentially no effect.
No effect at all.
Yeah. So I'm just saying the rotation rate of the Earth is susceptible to all these small effects that can add up, and we deal with it. We throw in leap seconds.
23 hours, 56 minutes, and 4 seconds.
That's our rotation rate to the stars.
To the stars.
It's exactly 24 hours on average, and that average is changing.
So it's way more complicated than you realize. When's the next leap second? Someone Google it, please. Someone. Jan, this would have been a chance for you to finally use your phone again. Yeah, Keegan, you could Google something useful. When is the next leap second? Is there one this year? Because I think if there was one this year, it would be cool, nerdily, at your New Year's party to add. Sorry?
Potentially June 30th next year.
Next June. Okay. But if you ever notice that there's a leap second and you're at your New Year's Eve party and you want good nerd cred, you can get them to delay the count by 1 second. Do your 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 1, 0, and you would be scientifically accurate. Just saying. We're going to finish with this, and then we're going to pause. Your homework is get caught up. What does B want me to find? The radius. We're in orbit. So geosynchronous satellites, they basically appear to remain motionless in the sky because as the Earth rotates, they're staying above the same location. Really useful for our communication satellites because then you know where a satellite is where you can bounce a signal off and have it hit somewhere else on the Earth. So the vast majority of our communication satellites, they're around the equator in a geosynchronous orbit, all at the same radius. What would the radius be? Well, we would have gravity is what's pulling me in a circle, but since it's period, we're talking about here, it'll be 4 pi squared r over t squared. M's cancel. I think I would multiply the r squared to the top. It would become an r cubed. I think I would multiply the t squared to the top. And I think I would divide the 4 pi squared. How does one get rid of a cubed? Cube root. So it's going to be the cube root of big G, big M. The period is going to be 8.61 times 10 to the 4th. Right from your formula sheet. Squared all over 4 pi squared. So now, get your calculator out, Keegan. What do you get? Cube root of answer button. I got, am I right? 4.22 times 10 to the 1, 2, 3, 4, 5, 6, 7. They're very high up there. And we've got hundreds of communication satellites up there. Is it going to get crowded? Are we going to need to worry about satellites crashing into other satellites? Well, how big is that circle at that radius? The circumference of a circle is 2 pi r, so it's going to be 2 pi times that answer. If I divide by 1,000 to turn it into kilometers, it's a circle that's over 250,000 kilometers in circumference. We have lots of room to put satellites there still. So we're going to pause with that. Your homework is finish up lesson 4 and 3, and you can start to whittle away at the ultimate review.